Hello and welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last few lectures we have discussed the concepts of logistic regression as well as softmax regression, and this allowed us to tackle classification problems of both binary classification and multi-class classification. And before that we looked at linear regression, which allowed us to develop the simplest possible ML model, and we also discussed ways of getting rid of overfitting such as ridge regression, lasso as well as elastic nets. We laid the foundation of overfitting using the bias variance trade-off, which also allowed us to understand the concept of underfitting. Now we are at this stage in this course where we can slowly start to introduce more and more complex algorithms. If you remember logistic regression or softmax regression, the linear part of the model, right, beta naught plus beta transpose x, is still at the heart of the logistic function or the softmax function. So in some sense we have not really gone beyond a linear kernel, right. However, many of the problems in core engineering disciplines involve non-linear problems. So how do we capture these non-linearities? That brings us to the domain of more complex models like decision trees, support vector machines, neural networks, Gaussian process regression, k nearest neighbors, and so on and so forth. Before we can do that, however, we need to understand various types of loss functions that are available to us while we train the ML models. So let's take a deep dive into the types of loss functions that are available to us as a person who is studying machine learning. So the topic for today is loss functions employed in ML models. Right, and as you already know, ML models are trained by minimizing a loss function to obtain the best or optimal set of model parameters. So these were the beta naught and beta vector that appeared in linear regression, ridge regression, lasso, logistic regression as well as softmax regression. So far that is the way in which we have studied, but like I said, we will also go to models that can handle non-linearities. Okay. Now what is this loss function? We have already studied this, but let us write it down so as to solidify our concept. A loss function provides a quantitative measure of the performance of an ML model. Okay, so we are able to quantify the performance of the ML model, and this it does by indicating the deviation between the true or actual value and the predicted value of a target variable. Right, and you know that this target variable can either be a continuous variable in a regression problem, or it can be a discrete variable in a classification problem. In today's lecture, we will look at both types of loss functions which are designed for continuous variables and loss functions that are designed for discrete variables. Okay. So, what are the loss functions that are employed in ML models? So, various types of loss functions are employed in ML models, and we will discuss them today one by one. The first loss function, as you may have guessed, is the ubiquitous mean squared error loss function, shortened as MSE, and this is something you are very familiar with, because when we studied the concept of linear regression, we worked with the sum of squared errors, which is just the number of data points times the mean squared error. Now, this mean squared error is also called the quadratic loss or the L2 loss, and this 2 here indicates the exponent of the deviation between the actual value yi and the predicted value yi hat, right. So, yi is the actual value or the true value, and yi hat, as you know by now, is the predicted value. Okay. So, this MSE is called the quadratic loss or the L2 loss. Now, why is it so widely used, right? Why do we keep on seeing this loss function used in most ML study? So, it is very widely used for two reasons: due to its mathematical simplicity, there are no complex functions involved like log or exponent and so on, and its easy differentiability. You can differentiate, right, the L2 loss very easily, right. So, that is the advantages. There is also some drawbacks, right. The drawbacks is that it penalizes the large errors more strongly. That happens due to the exponent of 2, right, that we have used in the loss function. So, it penalizes larger errors more strongly, and thus is sensitive to the presence of outliers. So, if you have a data point that accidentally due to some error is an outlier, then that point will end up influencing your loss function a lot, right, and this is something you may not want, although in some cases it could prove to be an advantage as well, right. So, these are the pros and cons of the L2 loss function, and there is one more of particular note that I also want to list here. That is that since the MSE is a convex function, it allows for analytical solutions for linear models like the linear regression we studied, right. Since the local minimum is guaranteed to be a global minimum, right. Whenever we are minimizing the loss function, we are trying to find the global minimum, right, the set of parameters that lead to the lowest possible values of the loss function. However, most minimizers, numerical minimizers we know, can only find a local minimum, right, and this is obviously a problem. However, since the MSE is a convex function, right, a local minimum is also a global minimum, and therefore, right, for problems like linear regression we are able to find an analytical solution, right. So that is a benefit. Okay. So let us go ahead and see how this is defined, and hopefully this is just a refresher and that you remember this expression from a few lectures ago. So I am going to denote the loss with capital or uppercase L. Subscript MSE means we are looking at the mean squared error loss function. This is 1 divided by the number of data points, that is the mean part of it, and then you have to write the squared error some I going from 1 to n, the deviation between the predicted value and the actual value whole squared, and this here is the exponent of 2 that I was referring to earlier, right. So n here is the number of data points, the summation also runs from 1 to n, this is the predicted value of the ith data point, and this is the true value of the ith data point, right. And like I had mentioned a few earlier lectures ago, you know that you can define this root mean squared error RMSE as the square of the MSE. Okay. So this is the root mean squared error, right, and the advantage is has the same unit as the target variable, right, and that is particularly useful, right, because if you are trying to predict a quantity like temperature, right. So if you are, let us say in your engineering discipline you wanted to predict the temperature, right, and let us say it is being measured in Kelvin here, right, your MSE unit will be Kelvin squared, right, and Kelvin square would not make sense, right, if you wanted to report an error that is incurred by the ML model. However, the RMSE unit would be just Kelvin, right, and then you can use that as a measure, right, of the error incurred by your ML model. So that is why the root mean squared error is very useful to be defined. It can be used as a measure of error in the predicted target variable. Okay. So that is all about how the MSE is defined. Now there is one more advantage of MSE, and that is particularly nice, right, from a statistical and probabilistic point of view. Let us see what that is. So the interesting point is that the reason for the MSE being preferred statistically is that it minimizes minimizing it is equivalent to obtaining what is called the maximum likelihood estimation parameters. Under a Gaussian noise assumption. Okay. Let us try to understand what this statement means. So, I am saying that minimizing the MSE, is equivalent to obtaining the maximum likelihood estimation, right, on the parameters under a Gaussian noise assumption, right. Now, it is very likely, right, in various engineering processes that the noise in the data, right, that is being measured is Gaussian, right. The Gaussian is a normal distribution and we have encountered it earlier. It's very it's very well encountered in engineering disciplines. So, thus if the true value is the predicted value plus some error, right, where the error or the noise is distributed normally with a mean 0 and variance sigma square, and this is something we have seen earlier, right, even when we derived the parameters, right, for the confidence intervals, then we made this kind of an assumption. So, these are the errors, right, or the noise that is Gaussian in nature. Okay. And as before, you know that yi is the true value, yi hat is the predicted, right, value. So, in this case then, if you wanted to write the probability of yi, right, being the true value given your predicted yi hat, that will be 1 over root 2 pi sigma exponent of minus yi minus y hat whole squared by 2 sigma squared. And this, you must remember, this is the normal or the Gaussian probability density function, PDF, right. Now, given that this is the PDF, you can write down what is the likelihood function, right. How likely is it that if you had the entire data set, right, you would be able to obtain y1, y2, y3, y4 and so on and so forth, right. So, the likelihood function is then given as L, I am going to use a cursive L for this, is the product I going from 1 to n P of yi given yi hat, right. And we can go in and substitute each of these probabilities here. They are all normally distributed and we are going to assume that these samples are independent and they are identical. So, let us go ahead and write this down. So, like I said, we are going to assume, right, independent and identical distribution for yi, and thus this likelihood function, which is the product of the conditional probabilities becomes pi I going from 1 to n, and this capital pi is a product symbol. It just means that we are taking the product of all the terms here when I goes from 1 to n, just like the summation symbol used for addition. This is the product symbol. So this is 1 over square root of 2 pi sigma squared exponent of minus yi minus yi hat whole squared by 2 sigma squared. Okay. Now if you take the log of the likelihood function, it makes it easier to work with, because you may remember that the log of the product of a set of numbers is the sum over the log, right. So for example, log of AB is log A plus log B. Therefore this product, when you take a log, it becomes a summation. So this term we can write as sum I going from 1 to n log of 1 over square root of 2 pi sigma squared plus log of exponential of minus yi minus y hat whole squared by 2 sigma squared. Now there are a number of properties of the log function we can utilize here. One of them is that a log of x to the power a is a log x. That can be utilized here because the square root is just to the power half, right, and that half can come outside. So the first term becomes sum I going from 1 to n, the exponent here is minus half, right, because the square root is in the denominator. So it is minus half log of root sorry, there is no root anymore, 2 pi sigma squared. Now for the second term, you know that the log and the exponent, they are inverse functions of each other. So essentially they counteract each other, and you are simply left with minus yi minus y hat whole squared divided by 2 sigma squared. Now this first term is just the same thing repeated n times. So it becomes minus n halves log 2 pi sigma squared, and then the minus again comes out of the summation. This is sum I going from 1 to n yi minus y hat whole squared by 2 sigma squared. So this is the log of the likelihood function. So this is the log likelihood. Okay. Now in optimization, right, you may remember that if you maximize a function fx, that is equivalent to minimizing minus f of x, right. Essentially multiplying by a minus makes the max to a min, right, and that is something we can exploit here, right. Essentially we want to maximize the likelihood that based on the measurements yi hat, right, or the predictions yi hat, the values yi are actually distributed in this way. So we want to maximize the likelihood of that. So if you want to maximize the likelihood of L, we can actually minimize the likelihood of minus L. But in fact we have something better here. Since the log is a monotonically increasing function, we can just work with the log of L. So in a sense maximizing the likelihood is equivalent to maximizing the log of the likelihood, because log is a monotonically increasing function. And this itself is equal to minimizing minus log of L, right. So, maximizing the likelihood is equivalent here to minimizing the minus log of the likelihood, and why we are doing this is because the log of the likelihood has a very simple expression that we have derived here. So, let us look at this expression carefully and see how we can go ahead. So, essentially we want to minimize minus log likelihood. So, that is just n over 2 log of 2 pi sigma squared plus some I going from 1 to n y I minus y hat whole squared by 2 sigma squared, right. Already something really interesting is emerging here. Look at this, look at what we have obtained here, y I minus y hat whole squared and then a summation, right. This is really nice because this is just right similar to the L2 loss function. And even more so because this part essentially is a constant, right, that does not depend on yi hats, right, and this as well, I mean you do not have any control on it. In fact, you can bring this 2 sigma squared outside the summation. So, essentially maximizing the likelihood we have been able to show is equivalent to minimizing the sum of squared error, right. So, this proves that minimizing the L2 loss gives you the maximum likelihood estimator, the maximum likelihood estimation of the parameters, okay, and therefore under a Gaussian noise assumption it is the most suitable loss function. The L2 loss function. So, I hope this discussion gives you a good feel for why the L2 loss function is so popular, what are its pros and cons, and what is the sound statistical basis behind choosing this particular loss function. Now, like I said, the outliers are sort of given a lot of importance in the mean squared error. So, there is an alternative loss function that can be employed, and this is called the mean absolute error, which is shortened as MAE. So, this loss function is also called the L1 loss, right, and this one, like in the L2 loss, refers to the exponent of the deviation between the target variable predicted value and the actual value, and it is more robust to the presence of outliers in the data set. Okay, than the L2 loss. So, how does this expression look like? So, if you want to define the MAE loss function, mean absolute error, that is 1 over n sum I going from 1 to n yi minus yi hat, right. Obviously, you can't write it just like this because errors can be positive or negative and they would all cancel out. So, what you need to do is make use of this word absolute that is there in the definition. So, you have to include the error between the true and the predicted value in an absolute value function. So, this is how the MAE loss is defined, and as you know, this is basically the absolute value function. Now, if you remember the plot of the absolute value function, it looks something like this, right. Here I am just plotting the absolute value of x versus x, right. It looks something like this. So, at this point, right, there is a derivative discontinuity. So, that is a drawback of the mean absolute error. So, this is derivative in 1D and in n dimensions, right, that we are working with, or p dimensions because we have p features, it leads to a discontinuity in the loss function gradient. So, although it is more robust to the presence of outliers, so it will not blow up the loss function in case you have a point that is too far, it has its own share of deficiencies, right. So, that brings me to the end of this particular lecture. In today's lecture, we covered the basics of the loss functions used in machine learning model, and this is going to assume more and more importance as we go into the non-linear models that machine learning has to offer. So far we were working with linear models, they were models that had analytical solutions. However, we discussed that even things like logistic or softmax regression, there are no analytical solutions and one must resort to numerical optimization. So, once we finish the discussion on loss function, then we will discuss on how we can numerically optimize the loss function to obtain the best set of parameters. Thank you, and I look forward to seeing you in the next lecture.